Good morning, everyone. Welcome to the EasyPower Tuesday Refresher. My name is Jim Chastain, and just wanted to remind you that you're welcome to contribute to the discussion this morning by either submitting questions or comments during the session. May not be able to answer them in the time allotted, but we'll respond to everyone via email by the end of the week. So today we're exploring the specific topic of calculating arc flash below 240 volts in EasyPower. And as we are wont to do, you'd like to start off each session with poll questions. And so this pertains to the topic at hand. So if you would please help us by submitting a response or contributing to the inputs here. Certainly there's no obligation, but we're trying to get a feel for how often your projects include elements of less than 250 volts. And here's how folks have answered this one. And then the next one is, how often do your systems or projects include battery systems? And this is an area that's coming up continually and is frequently a complicating issue in this whole discussion about low voltage arc flash. Share this one. Thank you. And then finally, how often are the DC systems less than 50 volts, 250 volts? We do appreciate the input and the feedback, and especially when you have questions regarding the tools. Before we launch into this, I just wanted to remind folks, if your maintenance agreement for the tools is current, then you have access to tech support via email or phone virtually anytime you need it. So make sure you take advantage of that. So thank you for your inputs. And some of this information is very interesting. So let's get into the topic and we'll see where that takes us. Now, for what it's worth, today's agenda reads more like a book report than an instructional video. And what I'm going to be doing is sharing some of the results of my research on the topic. One of the things I'd like to mention is that frequently when we're talking about arc flash calculations, there's a misunderstanding about the precision involved. You'll see in all the literature and all the reports on arc flash, they refer to estimates as far as the results because there's a fair amount of variability in the test data that was used to predict the model. And when it comes to voltages lower than 250 volts, things got really off the map. And so that's why there wasn't as much time spent on analyzing the low voltage arc flash when the initial model was developed. So that's why we're talking about this. There are some varying opinions on how to deal with low voltage calculations. So what I'm going to be stepping into are details on several of the industry standards that we have to rely on, and then some more recent independent test results that are intriguing nevertheless. And I want to emphasize that this is not a recommendation on how to do anything specific, and in particular, without knowing the specifics of your system, it's impossible to make recommendations. So with that, I want to emphasize the fact that engineering judgment is the bottom line for this whole discussion. All right, so when we look at NFPA 70E is kind of the baseline or the standard for arc flash calculations in general, this is the place where the 2-second rule came from, which basically says assume a 2-second limit on calculation time if no protective device is known. Now this applies to virtually the whole system, and so I'm always queasy even referring to this, but it's there nevertheless. And the point is they consider, or they being the standard, considers 2 seconds as a reasonable maximum time for calculation based upon a human being able to remove themselves from the danger zone if it were continuing. Now, even with this, they recommend, they being an FPA 70E committee, recommend that sound engineering judgment should be used in applying the 2-second maximum clearing time. This is also the document that recommends the use of what's called the max power method when we're calculating DC arc flash calculations. That's, again, not saying anything other than that's where you find this information. Now, when it comes to the IEEE 1584 model that was initially published in 2002, the recommendation is to use the model over a range of voltage from 208 volts to 15,000 volts. And that includes any frequency between 50 and 60 hertz, voltage fault current ranging from 700 amps to 106,000 amps, and then gaps between conductors ranging from 13 millimeter to 152 millimeter. And again, this model from IEEE 1584 is based upon 3-phase faults. No more than a paragraph later, after talking about the application voltage range, they say, well, of course, the 208 volt accuracy is not in the same class as a 250 volt calculation. And what they mean by that is that the results anywhere below 250 volts are more conservative, and by that they mean the results are going to be much higher instant energy. So the question becomes how much higher, and that's why we're kind of left in the lurch on our own devices. IEEE 1584 also goes on to talk about the 125 kVA exclusion, and that basically implied or stipulated that equipment below 240 volts need not be considered unless it involved at least one transformer greater than 125 kVA in the supply for that system. Now, the contrapositive or the corollary to that statement is, well, if IEEE considers this inconsequential, then systems, it could be implied that systems supplied by this voltage level and in systems with less than 125 kVA transformers could be considered to be at least no greater than 1.2 calories per square centimeter as energy level, or else they would be included. And then secondarily, the 2-second limit on excessive incident energy calculations when no available protective devices are available. That's almost gets into another category. Now, the bottom line is they admit or publish that they had limited testing below 250 volts. In fact, they only had one test at 208 volts where the arc actually sustained itself for any period of time. Now, in the application note that was released in 2013, labeled IEEE 1584.1, they include the scope of study should be broad enough to include 208 volt panel boards, all systems down to 208 volts AC equipment for maintenance purposes. So that's old news, I admit. Now, if you look at the most recent version of the National Electric Safety Code, you'll see that in table, and that's C2, table 410.1, they have a list of recommended clothing ratings based upon equipment and voltage level. Now, and to be fair, I'm kind of picking and choosing specifics from each of these documents, and so I'm not trying to shade anybody's take on this. I'm just sharing information, and by all means, I'd encourage you to get in and look at more of the details in each of these documents if your system requires it. But in this regard, they recommend for equipment below 250 volts, network protectors, they recommend using 4 calories per square centimeter, panel board, single phase, 4 calories per square centimeter, and panel boards 3-phase at 4 calories per square centimeter. Likewise on meter cabinets, oh, I got a typo. The equipment ranges from 50 to 250 volts on this list as well. Pad-mounted transformers, CT meters and controls, pull boxes and open air systems, again at 4 calories per square centimeter. Then if we take that, bring that a little bit more current, as far as the test results, some Merson engineers investigating factors affecting the sustainability of arcs below 250 volts produced a very well-detailed report, and this is literally just one figure from a 12 or 18-page document. Oh, and by the way, I will be more than happy to share my list of references or bibliography for this book report if you ask for it on the list of questions. So, but what they reported is that if you look at 208 volt arcs with different available fault current, and interestingly enough, with different available bus material, you have a little bit more better view of what's going on with this low voltage arcing situation. So essentially below 4,000 amps, they couldn't get an arc to sustain at the 208 volt level, and then above 4,000 amps, the arcing time, the extinguishing period, lasted no more than a second, and in some cases quite a bit less than a second. Now again, this is just data, and whether it applies to your system or not is something that you need to investigate. Then if we go a step further, in 2017, this paper was presented at a safety workshop at IEEE, and this focus was on the effect of air gap on the duration of a low voltage arc. And so this one particular chart, again, an excerpt from a complete report, which is, I think, worth investigating and taking the time to read. But this shows at 208 volts, with a wide variety of available arcing current, that the arc duration in cycles for, in this case, ½ an inch up to 3 inches, lasted less than 6 cycles, even in a worst case scenario. So we had a 40,000 amp that lasted less than 6 cycles, if I'm reading this correctly. Maybe it was up at 9 cycles for 40,000 amps at ½ an inch. So again, at very low currents, which is what we usually see in the 208 volt range, the arc duration was very short, and in some cases wasn't existing at all at extended arc gaps. Then, courtesy of the BPA, some testing that was done on some DC circuits, specifically 125 volt, 1300 amp hour battery system, which was able to produce voltage faults of 3,900 amps and 7,800 amps. The longest arc time that they were able to produce was 715 milliseconds. And if, again, as you read this report, they conducted it very much like the original IEEE testing 10 years ago, which they set up the array of calorimeters and measured energy as they induced the arc with some measured amount of current and voltage. And so what they were able to determine in this 125 volt DC system, that they measured the incident energy at 18 inches to be 0.9 calories per square centimeter. But if you use the max power method that's recommended by NFPA 70E, the calculations end up being 10.3 calories per square centimeter. So the bottom line to the BPA report is that the model is conservative to the point of being a factor of 10 off when it comes to actual comparing it against actual tests, at least in these areas of voltage and current. Then another test report that was released in 2010 by an engineer at EPRI was specifically on 208 volt network protectors, and the results show that in 14 tests on two protectors at 208 volts, they sustained no arcing. At 18 inches, the maximum energy was 0.02 calories per square centimeter, no sustained arcing. And 11 of the 14 tests self-cleared in less than one cycle. Longer fault, when they initiated the fault with a tool bridging the gap, they found that the maximum time once the tool was removed, or that the burn ablated away some of the material that was involved in the arc, that the arc again was self-extinguished in 6 cycles or less. So their recommendation, the recommendation of this particular EPRI report, is that 4 or 8 calorie clothing is sufficient protection for this 208 volt environment. All right, so that's my research, and again, it's a sample. Didn't have time to go over all of it. The point I wanted to make at this point, though, is that the models are very conservative that we're using to do the calculations. EasyPower is a tool, and it allows you, the engineer, to customize the arc flash control settings, and permits calculating time constraints, both globally and locally, and then energy constraints locally. So what I'd like to do is to jump into the EasyPower tools and show where these are implemented and where to verify the results match what your system requirements are. And at this point, I'd like to reiterate the fact that these are not recommendations as far as a system approach, because that needs to be done on an individual system level. But let's get into the tools and talk about this. All right, so what we're looking at here is a larger system that has 208 volts supplied both by a 75 kVA transformer and by 112.5 kVA transformer. And just with the basic setup, and we go into arc flash calculations, and what I recommend actually in any system that I'm doing analysis on is to look at the current first. And you'll notice that was the baseline for most of the reports that are and the research being done. And so what we see here in this system, in my 208 volt line, I've got a maximum of 3,200 amps during the first half cycle. And in this system up here from a larger transformer, I got a maximum of 4,798. So these numbers are borderline as far as some of those reports that we were looking at, borderline being in the range of self-extinguishing when it comes to an arc flash at that voltage. Now, we're not talking about the air gap here, and that might be something I'd want to look at before I made any changes to the system. But if we do calculations just based upon those raw numbers, we see that we have 5 calories, 4.2 calories. In fact, I think I've made some adjustments in the system already. So let's go ahead and look at that. I'm in the short circuit focus. I'm going to look at the short circuit options. And under the short circuit options, we're going to look at the arc flash hazard tab. Now, when I talk about globally, this is where all the global adjustments are made. Normally, when you start a new project, these ranges here for max times will be set at 1,000 each for each voltage range. And as I do that, and I go back to my report, my results, I can see that it has an influence. Without that limitation, we're talking 43 calorie calculations, 16 calories, 16, 18, and then up here on this larger transformer, 365 calories. I also recommend at this point, before I jump into too much anguish, is to go in and look at each bus and what the calculations and protective devices involved are doing. I'm not going to worry too much about this transformer bus, but I do want to look at the calculations for this panel. So what we see, it's a 208 volt system. The protective device is BLD3H4, which is the breaker upstream in the feeder panel feeding the transformer. We see that the air gap is 25 millimeters. Voltage fault current, we already discussed, was just under 3,200 amps, which puts us on the borderline of not even sustaining an arc itself, and yet we're allowing the tool to calculate out to almost 3.5 seconds. And that's the reason that we're getting high incident energy. So the first place of control or adjustment, because I'm not too worried about that, and let's look at this one. I've got the same thing where it's an upstream breaker above a transformer that's tripping, 25 millimeters arc gap, 4,800 amps voltage fault current. Again, borderline on a self-extinguishing at all. I personally feel comfortable setting my maximum calculation time to 1 second. Now, the trade-offs here is this is a global setting. So what I'm doing is setting for systems less than 250 volts, a 1 second maximum time, knowing that this affects both AC and DC circuits. Let's go ahead and do that and see what that results in my system. It shows here, if I fault this, we're still above 15 calories. And if I fault these systems down here, we're down below 6 calories, which may or may not be adequate. And if I look at the arcing current, again, it's well below the 2,000 amp self-extinguishing level at the 25 millimeters. So this brings up the point, well, should I just kind of keep reducing the global settings, or should I go and look at these individually? So if we go in locally, if I go back to database edit and look at my data dialog box for this particular panel, the center one, which is a little bit higher, each element in the system has an arc flash hazard tab in its data dialog box. And again, right now we're following the global settings. If I want to set this particular device to be calculated at a different time, I feel comfortable saying, okay, well, this particular system, based on the current voltage and air gap that we're looking at, justifies a setting of 0.75 maximum. And as I go in and fault this bus, I can see it's at 4.1 calories. Now this brings up another question. What is company policy? The standard says these systems, because this is supplied by less than a 125 kVA transformer and it's 208 volts, the IEEE 1584 says this is negligible, which relates to an incident energy of less than 1.2 calories, which again reflects the fact that the calculations going on are considerably conservative. So based upon IEEE 1584, I'm confident in assigning this particular device an incident energy of 1.2 calories or less. The way I would do that is, again, under arc flash, go to forced, 1.2 calories. Now again, it's going to show me the arc flash boundary setting, and in this case, if 1.2 calories is the limit, then 18 inches is the working distance and the arc flash boundary. So now as I do that, I show an arc flash boundary of 1.2 calories and 18-inch arc flash boundary. Now, what's the trade-off in doing that? Well, first of all, let's go back to I've done this based upon company policy and the assessment that these current levels and voltages and air gap involved are well within the boundaries of the recommendation in IEEE 1584 that this is a negligible arc flash hazard. What I would like to do is say, or make a notation to myself that, and I might say something like arc flash hazard minimal based on IEEE 1584. Now, the same thing could be said for this system up here, even though this is higher than the, well, this is on the borderline of being 125 kVA, I might not feel comfortable making this 1.2 calories, although that's what the standards say I can do. I might actually want to rely on the C2 recommendation, which says all 208 volt systems, any system below 250 volts can be rated or worked on with a 4-calorie protective clothing. And so I can either put in the arc flash boundary or working distance. And in this case, when we come back and do our short circuit and we fault this bus, now we get a 4-calorie rating and an 18-inch working distance. Again, I'd want to document how that setting was made. I want to train the people to understand why this is 4 calories and the fact that they need to make sure they're protected to that level. And over here, I guess the one was the one down below it, I'd have a 1.2 calorie. Now, and again, I go back to the company policy. If I want to have 4 calories as the baseline for all day-to-day clothing rating, that might enter into the decision as far as what the label is going to say on these panels. Okay, it seems like I kind of stumbled through that, but the bottom line is, in short circuit, I have the access to short circuit options. Under short circuit options, arc flash hazard tab, I have the ability to control globally the calculation time for any arc flash calculations by voltage range. And again, this is where the 2-second rule could be invoked if we're having problems with higher voltages, but this is also what would limit the calculation time on all 250 volts or less than 250 volts. Then when I go to the individual arc flash tab of any system element, data dialog box, we can override the global settings by putting in a forced level of incident energy, or by limiting the calculation times for this bus to a specific level, again, which would override what's going on at the global range. Okay, so that's what I wanted to cover. Let's see if we did everything we meant to do. So the point I'm trying to get across is that the models are conservative, admittedly so, and the bottom line is they produce higher incident energy at voltages less than 240 volts. It is encouraged that sound engineering judgment be applied based upon specific system parameters, and rather than a one-size-fits-all approach, understand what your system limitations are and whether or not you need to make adjustments either on a global basis or a local basis. So I appreciate everyone attending. By all means, check out the new EasyPower website. We have new training sessions announced and some new online training available. And we appreciate your attendance. Again, we're running out of time as far as questions, but we will answer them via email. Have a good day, and we'll talk to everyone next week.